Alright, so now I'm going to explain on our first question for our individual assignments. First question. So, as you can see, we have given a circuit here. So, based on electronic circuit given below, we have to use one of the simulated tools such as Tinkercad or Multisim. But at for this question, I'm using Tinkercad because I'm quite comfortable with it. We're going to use this simulation to identify these parameters, IA, IB, ICVA, and VB. So after that, we're going to do some manual calculation, which I will be showing it later. After that, we're going to record some simulation works for our simulation right here. And yeah, I think that's basically what our objective is. So let us see our circuit first. So we have battery 9 volts going to the first 230 resistors, and we have one junction here which divide the currents into two separate lines. For the first line we have 230 resistor and also the 100 ohm resistors, and for second line we have 1 kilo ohm resistors. So I'm going to show a bit of manual calculation here. So our first step, I'll be using some basic resistors parallel resistance equivalent formula, which is for the first part, I use parallel. As you can see, this 1 over 330 plus 100 plus 1 over 1000, and then it's divide everything, and then we have plus 330 for this resistance right here. Then we have our total, equi total equivalent resistance, which is around 630.6993. Then we use some Ohm's law to find the total currents of the circuit. After that, we use Ohm's law again to find the voltage A, which is the voltage across the 330 resistors to find the voltage, and we have this 4.7 volts. After that, we take the battery's voltage minus the voltage A to find the second voltage, which is around 4.2909, which will be our voltage B, because we know that in um here both of these leg will be we have the same voltage because this is a parallel circuit. After that, we use Ohm's law again to find the B current. We have around 4.2709 milliamperes. And after that, we use for IC, we're using some Kirchhoff current law, which state that every current go in must equal to every current go out. So we have 14.27, which is total current, minus the B current, which is 4.29, and we have 9.9791 milliamperes, which is the current for C. And this is a summary of the answers. I've written it so we can see more clearly. And finally, we can use some KCL check, Kirchhoff current law, to state that the calculation is actually correct. So 4.27, the current entered, and equal to current out, which is 14.27 current out. So it equals current in equal current out, so our calculation is correct. And moving on, we have our simulations. So for voltage A, we can see that, okay, so how the current work is actually, so we have from positive 9 volt battery connect to the first 330 ohms, and then it divide into two line, which is first line is 1k here, and the second line is 330, and it's a 100 ohms here. So the first voltage is our voltage A, which measured across the 330 ohms, which state that 4.7 volts is being measured. And for second one is voltage B. We can see that how it measures is through the 1 kilo ohm resistors, which I put from the head of the resistor to the tail of the resistors. So we have 4.28. For the current A, we can find is actually the total current of the circuit. How do we find is actually the tail of the how do we find total current is we put one end of the tail of the multimeter into this 1k resistors, and also the other one to 330 ohm resistors. So we have a total current of around 14.2 milliamperes. And the same can be said for our IB currents, which we can measure from the head the tail of the 330 ohm resistors to the head of 1 kilo ohm resistors. So for IC, finally, we can use it from the from the tail of the 330 ohm resistors to the head of the 330 ohm resistor, which is the opposite side of the tail. So let me show some secure simulation here. Okay. So as simulation is running, we can see that our voltage amperes is correct. Is currently running on 4.7 volts, which is around the same with our manual results, which is good. And after that, uh, the current went into this junction, which divide into the two separate line, which is 330 ohm line and the 1K line. So this IA we can see that it's 14.2 milliamperes. We can 14.2, but if you compare to our manual result, which is around 14.27 milliamperes, quite far, but it's still in the range. And the next one in line is we have our IB IB currents 4.28, which is quite similar to our manual result, which is I calculated is around 4.29. And last one is our voltage B 4.28, which is around the same 4.29. I would say is quite the same as our manual results, quite good. And last one we have IC, which is 9.96 when the simulation is running. And our manual result is showing around 9.97, which is quite close, I would say, which is good. And this is how the circuit will look like if it's running. Um, okay, everything is quite, no, it's quite, I would say it's quite not neat, but uh, we done the work because this is a simple circuit. First, battery go into 3309, and then we have a junction here which divide into two lines, one to 1K resistors and the other is a 230 ohm resistors, and these two lines connected to the negative terminal of the battery. So as conclusion, I can say the estimations are very close to manual calculation results, which is very good. And small difference occurred due to rounding in the simulator because in Tinkercad usually they round off the numbers, so it can be quite different from our manual results. So the circuit also satisfies the Kirchhoff's current law, which show that um, the final answer that we have just now, we can define it or we can test it with KCL, and we can see that the current in is equal to current out. So the conclusion is correct, which is good. And since the total current in is approximately equal to the sum of branch current IB plus IC, so the simulation verifies the manual calculation of this simulation. So we can say the simulation is quite accurate, which compared to our manual results. So I think this is a good sign, and I think that's all for me. Thank you.